In this video, we will learn about friction, chapter 8, topic 8.1 and 8.2. Characteristics of dry friction and problems involving dry friction. Now, why is it called dry? Because we are not talking about any lubrication, because when the lubrication is applied between sliding surfaces, then the friction dynamics is different. For this part of the lecture, we'll talk about dry friction, that is without any lubrication. So understand the characteristics of dry friction, draw free body diagram including friction, and solve the problem involving friction. Now friction is very important part. Without friction, we cannot drive the vehicles, we cannot grip objects, we cannot walk. In fact, we cannot pretty much do anything without friction. So friction is actually good for us because it let us hold the objects, it let us walk, it let us drive, and so on. A friction force always acts parallel to the contact surface. If a block is stationary, then the friction force acting on it is, normally we say that it's the coefficient of static friction multiplied by normal force, but that's not always the case, because that's the maximum static friction. Typically, when the block is not moving, when the force is applied, that means friction can be anywhere between 0 to maximum static friction, that is less than or equal to mu s time n's, where mu s stands for static. That means this is the friction max where the block or any object is not in motion, and when the object is in motion, there is still friction between the object and the sliding surface, and that's called kinetic friction, mu k, where k stands for kinetic. Applications in designing a brake system for a bicycle, car, or any other vehicle, it is important to understand the frictional forces involved. For an applied force on the bike tire, brake pads, how can we determine the magnitude and direction of the resultant friction force? So when we actually pull the brakes, the force is applied between the brake shoe and the tire rim, and because of that force, the friction acts in the opposite direction of that. And how can we actually design the brake? That's one of the application of friction. While moving heavy furniture, for example this refrigerator, then in order to move the refrigerator, is it best to pull up as shown, or pull horizontally, or pull down? So should we pull this up, should we pull straight, or should we pull down? What makes sense? And how far this string should be from the base of the refrigerator so that it can actually slide without tipping? So those are the questions that we can answer by understanding the concept of friction. Let's consider this block with weight W. Initially, the block is not in motion. Let's say there is no force is applied and the block is in equilibrium. At that time, the normal force acting from the surface balances the weight. So normal force is equal to weight. Now, when force P is applied, a normal force passes through the centroid of the block. But when force P is applied as shown in this direction, the normal force redistributes itself. And this is the distribution that we get. And because of this redistribution, normal force, the resultant normal force, now when we reduce this redistribution, then that redistribution results in the normal force away from the center of the block, so at some distance x. And now this is applied force P, this is friction force F, this is weight W, and that's the normal force N, which is not in line with W, it's at some distance x. So for the body shown in the figure to be in equilibrium, P should be equal to F, that is sum of the forces in horizontal direction is 0. That's only possible when P and F are equal. Sum of forces in vertical direction is only possible when N and W are equal. However, that does not guarantee equilibrium until the moment is also balanced. That is the moment at point O because of W, which is W multiplied by, or W multiplied by X, and it's P multiplied by H. When that moment at this point, when W multiplied by X is balanced by the P multiplied by H, then the system is in equilibrium. Let's look at it one more time. So the moment here is moment at this point. because of W. Now when we calculate the moment at this point, there is no moment because of the normal force and the friction force, because they both intersect at that point. So it's only because of W and X. So it's W times X, that's counterclockwise, and that's positive, and P times H is clockwise, so it's negative, is equal to 0. So sum of moments is equal to 0 when the block is in equilibrium. That means W times X is equal to P times H. So these are the three conditions that should be satisfied for a block to be in equilibrium. Means it's not moving. Now when the force P is applied initially and the P is increased gradually, the friction also increases with P. At some point the friction is maximum, and that value of friction is called the maximum static friction, and it can be calculated by multiplying mu s times n. Now that does not mean that when we apply the force and an object is not moving, the friction is this value. No, it's not. It can be anywhere along this line and the block will not be in motion. So do not assume that when an object is not moving, the friction is maximum static friction. No, we cannot guarantee that until we have been told during the problem solving. And this is the point where the motion first starts, and when block starts moving, the friction drops, and then as we keep on increasing the value of P, the friction remains pretty much constant, and that's called kinetic friction. Typically kinetic friction is lower than static friction because things in motion require less resistance than objects that do not move. Okay, so this characteristics is called friction versus applied force. So as applied force increases, friction increases, and at some point it's maximum. That's called maximum static friction, and then the motion starts. Okay, and when the motion starts, this is the free body diagram where we have friction, we have normal force, and the resultant of this too is Rs, which makes angle phi with respect to the vertical line. So it's very important to note that the friction force may be less than the maximum friction force. So it's just because the object is not moving, don't assume the friction force is at maximum value unless you are told or no motion is impending. If we need to determine this value of mu s experimentally, if the block just begins to slip, the maximum friction force Fs is mu times n, where mu is the coefficient of static friction, and we can determine this experimentally if we know the angle, and tan of that angle is mu s, this resultant force here. Now when the block is at an angle theta, then the weight of the block acts vertically downward, which makes an angle theta with this line perpendicular to the surface. So we set up our coordinate system x parallel to the surface and y perpendicular to the surface. And here are the different forces. So the weight of the block wants it to move down, but the friction force prevents the block from sliding down. So the block is in equilibrium, so it's not moving. At that time, this is the value of maximum static friction when the block is at the verge of motion. W is the weight, N is the normal force, and when we apply the equations of equilibrium, sum of forces in x direction and sum of forces in y direction with respect to this x and y axis, we get this equation. So for vertical motion, W cosine theta is in the negative y direction and N is in the positive direction, is equal to 0. And for horizontal forces, friction minus W sine theta, so W sine theta acts in this direction, that's equal to 0 as well. So the system is in equilibrium. So the steps for solving equilibrium problems involving dry friction: first step is to draw the free body diagram, indicate all the forces that are applicable, define the friction depending on the direction of the motion. Friction acts in the opposite direction of the motion. Determine the number of unknowns. Do not assume that F is always mu s times n unless the impending motion condition is given. So whenever the problem states that the object has impending motion, that means the static friction is maximum. Apply the equations of equilibrium and appropriate frictional equations to solve for unknowns. So remember, we have these three equations: sum of forces in x, sum of forces in y, and sum of forces in sum of the moments equal to 0. along with these three equations, now we have one more equation when the motion is impending, that Fs is mu s times n. Now this is another topic where, let's say, a person applies the force on this like heavy furniture, let's say this block, at some height h. So force P is applied at some height h. Now, depending on the magnitude of force and depending on the height at which it's applied, either this furniture will slide or it will tip, and we can apply friction equations to determine which will happen first. So when the force is applied, will the furniture tip before it slides or it slides first? And that literally depends on how much force is applied and at what height it is applied, and how the normal force is being redistributed. So when the force P is applied, normal force redistributes below the surface of the block, and as long as this variable x is within half of the width of the block, it's within b/2, then the furniture will slide. But when x is equal to b/2 or more than that, then furniture will tip. So this is the condition for sliding, this is the condition for tipping. Okay, let's look at another like that's so this refrigerator P, the force refrigerator is shown here and the force P is applied. When force P is applied, either it slides or it tips. And how do we know which one will happen first? So when no force is applied, this is the normal force below the surface of the refrigerator. And now when the force P is applied, the normal force redistributes itself and slides towards the corner in this direction. Okay, so this is the new position of the normal force relative to the center line, and this distance is called x. Now as P increases, n slides further and further in this direction up to the point maximum it can slide is this corner point. And when that happens, as long as the n is contained within the half of the fridge width, then the fridge will slide, otherwise it will tip. Okay, and the sliding and tipping depends on the value of the applied force, height at which the force is applied, and the coefficient of friction. So it's being decided by three factors, whether it will tip or slide: P, H, and mu. So now we can go back to previous presentation about friction, and in order to check whether it will slide or tip, we need to check two conditions. First, we assume that the slipping will happen, and at that time the static friction is maximum, and we calculate the value of x based on the equations of equilibrium. And if this x is below b/2, then yes, slipping will happen. And then second thing is we assume tipping happens. At that time the x is equal to b/2, and we will solve for p, n, and f. And we will make sure that the f that we get from this equation by assuming tipping is less than mu s by n. Okay, so there is one example whether sliding will happen or tipping will happen at first in the slide. You can just look at it based on the concept that we have discussed. Let's look at another example. We will actually solve the problem in the next class, but for now, just focus more on the theoretical concept of friction. The automobile has mass of 2000 kilograms, so which will act from here. So it's 2000 center of gravity multiplied by 9.81 newtons, and the mu s between the tire and the surface here is 0.3. Find the smallest magnitude of F required to move the cars if the back brakes are locked and the front wheels are free to roll. So brakes are applied here and these wheels are free to roll, so we only consider the friction at B. So the steps are: draw free body diagram, identify unknowns, and apply equations of equilibrium. So weight is one force, F is another force, normal force at front wheel. There is no friction at front wheel because these wheels are free to rotate. There is normal force at back wheel, and since the car is being pulled in left direction, the friction is applied in the right direction, and that is FB. Okay, so our unknowns are 1, 2, 3, and 4. So we have 4 unknowns. That means we need 4 equations, and 3 of them are our well-known equations of equilibrium, and the 4th one is our friction equation, mu times n. And using those 4 equations, we can solve for 4 unknowns. Thank you.